So I guess basically when I was developing my engine, I reached a point where I realized that I wanted to add particles to it, because I wanted effects like rain, or yeah, rain, smoke, and so on. So I decided particles would be a good solution for that. And then I did a little bit of research on particle systems. I saw Learn OpenGL had a particle system, but it wasn't satisfactory for my needs, I guess, because if I wanted to use particles for like rain or snow, then I would need to be able to have lots of particles, like millions. And um, so yeah, that's the setting for this. So yeah, naive CPU implementation. So you have a basic particle struct with some attributes. Here I have color, position, and velocity, and then a simple member function for updating the simulation, where it just adds velocity to position. So if you wanted like rain or something, you give it negative y velocity, and then go down for each update. And then particles are held by particle emitters, and particle emitters specify properties about how the particle should spawn. So since the only attributes particles have are color, position, velocity, I just gave each particle emitter minimum color, maximum color, min position, max position, min velocity, max velocity. So when you actually spawn a particle, it'll just choose randomly between these ranges what attributes the particle spawns with. And then the particle emitters also hold how many active particles there are, or the max number of particles, depending on how you want to interpret this. And then a buffer that lives on the GPU that holds all the particles, because we need to update the particle. Basically, it's the batch of particles. So you can do one draw call to render all the particles. Because if you have a million particles and they're all separate game objects, and you'll do a million draw calls and it'll lead to really bad performance. And then the simple function to update the particle emitter, it just takes a particle emitter. It gets a map pointer to the GPU buffer, and then updates all the particles in that buffer, and then unmaps the pointer. So the particles live on the GPU, and that's why we have to get the map pointer to update the particles. And then finally, we have render particle emitter, which just takes emitter and binds all the necessary stuff to draw, and then does one instance draw call. So that's what a naive CPU implementation would look like. And there's a few problems with this that I outline right here in the blog. First of all, in implicit APIs like OpenGL and DX11, mapping a buffer can actually be really slow, because you have to wait for the buffer to be done being read from on the GPU before the CPU can receive the map pointer. Otherwise, you can have data race. However, there is a partial solution to it called persistent mapping that newer APIs have, which allows you to manually synchronize the read and write on the GPU and CPU. But the problem is you have to multiply your data. So you can read from one buffer basically on the GPU while updating another one on the CPU. So it's still not the optimal solution for us. And then finally, we have that if we're going to have millions of particles and we have this single threaded loop, like even though the update is really simple, it's just incrementing position, basically, it'll be slow with enough particles. And if your particles are more complex, because you can add more fields to the particle struct and make the update function more complicated, and that will just hurt performance if the more particles you have. So yeah, that's a problem with the CPU implementation. And here's a diagram of what might happen if you map a buffer every frame in an implicit API. The CPU will do work, and then there'll be a big bubble underneath it where the GPU is doing no work, because we'll have to synchronize the reads and writes. And so what we do want is for the CPU and GPU to both be doing work simultaneously, but we want to avoid this situation. So looking at how we actually use the particles, we notice that every particle is the same basically in terms of what we do to it, how we transform the particle data. And no particle is dependent on the state of another particle, which means that all particles can be accessed or updated independently. And the third thing is that all the particle data lives on the GPU and is consumed by the GPU. So that means the CPU doesn't actually need to be very involved in this process. So yeah, multi-threading is good, but you still have a problem of the particle data being on the GPU, which is really far away. But yeah, if only there's a way to execute arbitrary code on a GPU. So yeah, what we want here is to use compute shaders to update the buffer holding all the particles. And that is exactly what I implement. Well, I didn't finish the write-up for it, but I can show code. Yeah. Is there a way to move this bar at the top? Oh, yeah, just check it. Oh, and I just noticed the comment by Owen. Yeah, I also like the styling. I use highlight.js to get that. Is this big enough for you guys to read?
Yeah.
Okay, so I need to find the file that has it. Oh, now I need to find an older version of the file, because so I have the update particle on the GPU, but this is with all the optimizations implemented, so it's kind of hard to read. Oh, I do have some fake code for updating it on the GPU. Actually, I think it's in the next blog post. Nope, scratch that. All right, sorry about that delay. So on the GPU, we can use a compute shader where each thread of it basically works on one particle. And well, it'll actually look very similar to the CPU loop, the difference being each thread only operates on one particle. Yeah, I'll show you the real, oh, I guess I should mention, yeah, so particles they have a lifetime as well in my implementation. So it means when the particle dies, we need to retrieve an index to basically indicate where a free particle lies, so that when we run the particle generation shader, which I haven't mentioned yet, that shader can know where dead particles are that it can overwrite. And this part can be ignored for now, because what we're going to do is draw every single particle in the buffer every frame. If you guys have any questions, feel free to ask, because this part of the talk is rough and incomplete.
Why you can't just use your instance count to infer your free count? They seem to be like
Okay,
it's the same information.
Why do I increment instance count?
And just like the instance is how many particles, instance count is how many particles you are alive, right? So why not just use that to represent free count? Instead, you have a separate atomic kind of count for that.
Because there are cases where we'll have particles that we won't draw and they will still be alive.
Okay.
But I'll cover that later. Yeah, thanks for the question. Oh yeah, and I'll also go over high level architecture of this. So I have in my engine, I have implemented an entity component system, and basically it means that if I want to give particles to an entity, I just need to attach or associate a particle emitter to it. So here's what the particle emitter component looks like. It just has, we can ignore this render flag for now, but it just has a handle to some internal data. That's something that I'm unsure of is the best way to handle this, no pun intended. But for now, I'll just have this handle, and then we'll have particle emitter parameters, which basically specify how the particles will look coming from this emitter. So it's similar to the code I showed you earlier, just more. You have acceleration, scale, in addition to velocity, position, color. Oh, and then we also have how frequently particles will spawn, and then the min and max life of the particles, how long they'll last before they get deleted.
What is this handle for? Just for ECS, or it have some closed fork?
The handle is, okay, so when I create an emitter, so I make a particle, or I make my entity first, and then I attach some boilerplate stuff to it. So for this example, I'm making emitter, a rain emitter that follows the player. So I attach it to the player as a child. And then right here is where I set the handle. I just have some function that generates a handle. Basically, I specify how many particles the emitter can hold, and then a texture, a name of a texture. And then it does some voodoo magic. to actually generate the handle. It makes a bunch of buffers basically. And then I do some disgusting reinterpret cast here. The details of this aren't important. Just I get a handle that I associate with all these buffers that I need for rendering and updating. But for the user, person who actually interfaces with this, they don't need to know specifics. They need to know, okay, handle, you know, don't mess with the handle or you get weird behavior. And then, yeah, then the user can just set all the parameters of the emitter, how they want it to look. This configuration, I have it so that it creates what looks like snow. Actually, I'll just run it real quick so you guys can see. Oh yeah, tell me if it like lags super bad, because I remember when Charles was streaming last week, it was super laggy. But yeah, you can see the snow is coming down. I'll go somewhere with less fog.
It is a bit laggy. Yeah, but we understand the point.
Yeah, video is not really coming through. The stills are coming through, but it's not.
Okay.
Yeah.
Well, if you want proof that it runs well, you can see it at 400 FPS right
now. Yeah, we believe you.
Well,
yeah.
I don't know if you can actually see that, but yeah, I'll close that demo for now. So yeah, that was 1 million particles with whatever number this is. Like that's the interval, how often particles spawn. Oh yeah, so then I have a system that updates particles basically every frame. The system is updated and it loops through kind of hard to read code when zoomed in this much. Okay. So I get all the particle emitters, and then, oh yeah, it's right here. Sorry about that. I get all the particle emitters, and then I loop through right here, all the emitters. And then there's actually 2 loops for this. There's one loop that generates the particles, and then there's another loop for updating the particle simulation. Again, the specifics of this aren't important to know. Just know that I'm basically calling running a compute shader in each of these loops. So that's spawning particles, and then I have a memory barrier because when I update particles, it's going to need to read from that memory. Yeah, just binding a bunch of stuff and then dispatching. So yeah. And then I guess now I can start going over some optimizations that I actually did for this. So the first optimization I'll be going over is in the Vertex Shader. Since all the particles have the same geometry, they're just 2D billboard quads. We can actually not have to bind a vertex buffer nor index buffer. We can generate the quad programmatically in the shader using just the vertex ID. And so that's what I do here. It looks kind of like magic, but I explain it a little bit in this comment. And there's also, I link a Twitter post where I got the inspiration for this from. or it's actually a buffer-free way to generate or to render a cube. So that's a little bit of a side note. So the advantage of not needing to read any vertex data or index data is that you free up some bandwidth, although not a whole lot because quads are not big in terms of geometry. But it also simplifies the rendering code. So now instead of having to bind vertex format, vertex buffer, index buffer, all we have to do is bind the particle buffer like we were before. And then we can just draw. We say each instance has four vertices, and we're drawing triangle fans. And we just specify the max number of particles of the number of instances we'll be drawing. Oh, and Leslie, you're wondering about the instance count of incrementing in the compute shader earlier. That's what we'll be introducing indirect drawing later.
In the chat, the chat asked you to.
Yeah, I paused because I was reading that. Sorry. I'm not doing a very good job at following the chat. Okay, so yeah, we should get a little bit of a performance boost from that, although it's mostly theoretical. I haven't actually profiled this optimization, but I have for the other ones, although I should mention I haven't actually put the results of profiling the other optimizations here yet. So I plan to do that in the future. But for now, you'll just have to go by my word, I guess. Okay, so the next optimization I did was using indirect drawing, because the problem with using the instance drawing approach is that since the CPU does, the CPU does not know how many particles are alive because the GPU controls that, and you don't want to do you don't want the CPU to read back information from the GPU because it's really slow, or it's either slow or has high latency. So you want to avoid that altogether. Luckily, modern graphics APIs have indirect rendering, which allows us to basically get draw arguments directly from the GPU from a buffer. So we can just say, I want to draw something, and the GPU will cover it for us. So what that fixes is needing to specify max particles here, because it'd be nice if we could render the amount of particles are actually alive instead of the max particles, because we might have 1 million particles that a buffer could hold, but only like 100 particles are alive. So pretty bad to render 990,000 extra particles. So yeah, we want to use indirect rendering, but by itself, it won't help us because the particles could be alive or dead in any order. And the draw arguments basically imply that you're going to be drawing an array of things. There's no drawing function that like takes a linked list of like, oh yeah, I want to draw this and then skip a few and draw this. and skip a few again. No, you just have to draw n things in a row. And so what we actually need is an extra level of indirection. So goes the famous phrase. So we have a new buffer called draw indices, which holds the particles that we want to draw, or indices of the particles that we want to draw.
What is restricted? Restrict. I never seen that keyword before.
It just means that the buffer won't be aliased in the same shader.
Okay.
So there won't be another buffer that like somehow overlaps with this. You're supposed to use it wherever you can, but I don't, and I don't know how much of a difference this has in the generated assembly. It's just you're supposed to use it wherever you can.
Okay, I see. So it's kind of like C restrict.
Yeah, it's really similar to C restrict. So yeah, we have a new buffer for indices of things, of particles that will be drawn. So, and we also have to introduce the indirect command, which holds the draw argument, because we're going to be, this is all so we can have indirect drawing. So these two new buffers, and then every time before we update the particles, we need to clear the instance count of the draw command, because we'll be incrementing that every time we want to draw a particle. So pretty much in every API, it's really easy to clear a buffer, and it won't introduce a sync point or anything. It'll go basically on the GPU timeline. It's not like mapping a buffer. So this will be quick. All this stuff is really ugly to look at, but yeah, you don't have to look at that. So when we actually update the particles, we have, if the particle just died this frame, we add its index to a buffer, so the particle generation shader can reuse it. And then if the particle is alive, we increment the instance count of the indirect command. And then that gives us an index that we can use to say, okay, now here's the location in our big particle buffer of a particle that we want to draw this frame. So it'll let us say that we want to draw exactly this particle, and this particle, and we can ignore the two dead ones. And so we'll only draw 3 particles instead of being required to draw the maximum amount. If there's any confusion with that, feel free to ask a question. Yeah, so with this, we gain the ability to select which particles are drawn on a per particle basis. However, because we have an extra layer of indirection, if we are drawing close to the max number of particles a buffer can hold, it'll no longer be sequential memory that'll be accessed, because we could the first index in the draw buffer might be pointing at the last particle, and then the second index could point at the first particle. they could point to any particle basically, and so you'll get these really incoherent accesses that can cause more cache misses. But despite that, we're going to keep this because the ability to finally choose which particles are drawn is vital for the next optimization, which is particle calling. So this is really simple. We just change the else in our code to say basically if the particle is visible, which is what all this is doing, if the particle is visible, then add its draw index to the indices list. And so with the rain example I showed, that can call over half the particles and make the rendering like way faster. This is one of the best optimizations, most effective ones I implemented actually. So yeah, even though it's really simple, give really good gains. And of course we can use a more robust method of calling if we want, but here I'm just using a dot product to say if the particle is sufficiently in front of us, basically, then add it to the draw list. Otherwise, it won't be drawn. Okay, then any questions about that?
That's a very cheap test. I like that.
Yeah, you could change the test to be like actual frustum calling, or probably not occlusion calling. That would be too much for just a single particle, but yeah.
Well, and two, you could almost you look at like a cone shape that would try and match the frustum.
Yeah.
I wonder if that would make sense. Is that basically what you're doing?
Yeah, the dot product is basically a cone shape.
Yeah.
So I have
it's within some angle.
So I have some magic angle that works.
Oh, awesome.
For most cases. I guess it's technically like the cosine of the angle. But yeah, you get the point, I think. Yeah, it's a cone in front of the player if the particle's in it. So it doesn't take into account the size of the particle. So if you have gigantic particles that are like a little bit outside the view, like the center of the particle is outside the view, then it'll get cold. So that's one downside of this, and that's why the calling angle is adjustable. But most of the time, you don't use particles to render giant billboards. You use them to render small billboards. So it ends up being fine to do it like this.
I like that. That's cool.
Yeah. And for the next optimization that I did is actually compacting the data, because right now each particle, or the particle buffer, is just a big buffer that holds a whole bunch of these structs. And you see position, velocity, acceleration are all vec4s. It's like they have this extra W component that's unused, and it's just so that you can get the alignment required for buffers for the stood 430 layout. So that's kind of gross. And we also have this extra padding in here that it could be hidden. Like if we didn't include this in, there'd still be this padding here. So we have all this wasted data, and the problem with that is that it wastes bandwidth when we're updating particles, and it also wastes our cache. So to load one particle, it takes up more than an entire cache line if the cache line is 64 bytes, which is the case on some architectures. So you'll get a whole bunch of extra cache misses and extra latency with all this wasted data. And also, of course, some of these things are more precision than necessary. They have velocity and acceleration. They don't need to be 32-bit floats because most of the time they're going to be relatively small values. You're not going to have a velocity of like 1 million, for example. That'd just be pointless. So yeah, usually be small enough to where a 16-bit half float will suffice. And similarly, color, we don't need the whole 128 bits for color. We can use just plain old 8-bit unsigned integers, and we can pack this down into a much smaller size. So to make this work, we'll be using GLSL packing and unpacking functions. So here is the result. So we still have position with full precision and also the unused W component. And then now we also have velocity, acceleration, and live packed into one UVec4. It says how to access the data. So the X component holds the velocity X, Y, and then the Y component of this holds the velocity Z and the acceleration X. And then the Z component holds acceleration Y, Z, and then the W component holds the remaining lifetime. And that's kind of confusing, but I guess I can show how that looks in code. Oh, not this one. This one. So it looks kind of gross, but it's worth it. We have this unpacked middle, which represents the velocity Z and acceleration X. And then we build them right here, just using a bunch of unpacks. And then, yeah, so it kind of gives us unreadable code, sort of. But it's all in the name of optimization, so it's worth it. And for actually generating, so I haven't showed this shader yet. This is where we actually make the particles. There's this nice function called make particle. And yeah, we use random numbers to get velocity, acceleration, and life, and then we just pack them into the variables. So that's how that looks. That's how interfacing with it works. Setting and getting the data. If there's any questions about that, feel free to ask. All right, cool, no questions. Then we can move on. So packing the data, reduced it to 40 bytes, which is really good. And I'm ignoring some extra alignment because we're not going to actually use the struct in our code. We're going to use an even better thing called SOA layout, or structive arrays data layout, which is laying out our data by how it's used rather than some arbitrary thing that helps us think of it more easily. So right now, our data is all packed into one struct, basically. Right? We'd have When we load the data, it's just like one line of memory. And if we want to load a bunch of particles, you can see that how it takes up cache lines on this imaginary architecture. So to load 2 particles, we need more than one cache line. See, the first particle is yellow and the second particle is this light green, and it bleeds over a little bit into the second cache line. So we need basically 2 cache misses in order to access this data.
Did you use Excel to visualize this? This is pretty good.
Yeah, I use Excel. So yeah, I talk about this in the blog. This is a memory access pattern. If we're going to be accessing multiple particles sequentially, yeah, to access 6 particles, we need 4 cache lines, which is 4 cache misses, which is a bunch of latency. So it's not optimal, as you'll see soon. Yeah, about every 1.8 particles read is a cache miss. So now let's look at how the shaders actually use the data that's going into the caches. So if we just need position, for example, we still need to fetch the whole particle struct and the whole cache line that comes with it. So we're not just fetching position from global memory, we're fetching position plus the rest of the particle plus whatever comes next in the cache or in memory to fit the cache line. So in the particle update shader, we're updating only the position and the velocity, and we access acceleration. And we're also accessing the lifetime of the particle. So what we're not accessing is the scale nor the color. And I have that in gray. So you can see this is wasted in the cache. So if there's some way to not waste this in the cache, then we'd be able to put more particle per cache line, if that makes sense. So we'd be able to reduce the number of cache misses we get. So looking at the vertex shader, we only need position, scale, and color. We don't need live velocity or acceleration. And you can see there's even more wasted data. So it's pretty bad, but fear not, for this section is called SOA layout, destructive arrays. Oh, it'd also be good to mention that right now the current layout is called array of structs because we have an array of particle structs. I think that's pretty self-explanatory, but it's not optimal, as you can see, because it leads to a bunch of wasted data, wasted cache. So we split up our data by how it's used. It ends up looking like this. We get 3 different structs, and they're labeled by how they're used. So we have shared data, which is accessed in every shader, or to access them both, the update and the rendering. So we'll have that by itself. And then we have particle update data, which is only accessed in the update shader. And this contains velocity, acceleration, and life. And then we have particle render data, which holds just the scale and color, because we only access this in the vertex shader. And so instead of one buffer with a single monolithic particle struct and holding a whole bunch of those, we can now have 3 buffers that hold instances of these structs. And when we actually put it into memory, it looks like this, and I color coded it by which data corresponds to which struct. And so now in the update shader, the particle update, we just need to access the data that's relevant to us, and then we won't be wasting cache on the stuff that we only use for rendering. So we can access the position, velocity, acceleration, and life, and you get much better cache behavior. And similarly for the vertex shader, we just access position and then scale and color, and you get basically 0 wasted data in the cache line. So you get pretty much more cache per cache.
Did you end up measuring this? I'd be curious to know how much of a difference it made.
Yeah, so
Second.
I just tell you that the most effective optimizations that I implemented were the calling optimization and then compacting data and putting it into this layout, structive arrays, structive arrays. So this actually gave a really nice performance boost. But hard numbers would be nice. So I'll provide those at a later date. I did measure performance, but I don't have the numbers on hand right now.
Yeah, the numbers plus the cache utilization ratio as well, if measurable. Those would be really good.
Okay. Do you know how I can measure the cache utilization ratio on NVIDIA?
Maybe. I mean, Nsight is probably your best bet, but not extremely familiar with the details.
Yeah.
So if anything, that will be your answer.
Yeah, I've used Nsight quite a bit, but I haven't seen that, although just probably not looking at the right numbers. Okay, so I'll go on to the next optimization, which is using shared memory in the compute shaders. So this is probably the trickiest one to explain, but I'll try my best. So right now, the problem we face is the abuse of atomics in their shader, which every thread performs 1 atomic increment, and atomics are not fast because of the incoherent nature of the low-level GPU caches. So like the L0 and L1 cache, they can't be invalidated by another thread. So basically it means that at best, an atomic operation will be performed in the global L2 cache, and at worst, it'll happen in global memory. And then you also add this to the fact that atomic accesses and operations from multiple threads must be serialized. So if you have 10 threads, they're all trying to increment the same counter. They're each going to have to wait for the previous to finish doing their increment before they can do their own. So it can lead to pretty bad performance. So what we want optimally is to use memory that is closer to the ALUs or the processors or cores, whatever you want to call them. And that's where shared memory comes in. So I have a picture, a little diagram here that shows the architecture of a compute unit in RDNA2. So you have the actual physical ALUs, and then you have this giant gray block, which is the shared memory. And you can see it's close in proximity to the processors. which is good. Not included in this picture is the L2 cache and global memory, but those are so far away that like they're basically light years away from the processors. And so that's how you can picture them. The problem with shared memory is that it's only accessible to threads within a work group as opposed to being available globally. So although shared memory is super fast, you have to design around it, around using it, which can be kind of tricky. Yeah, so main problem is local to work group. So previously we would basically just use atomics whenever we needed to get a draw index or a free list index in any thread. And it worked, and it was actually pretty fast, but it wasn't optimal because we're doing atomics in every single thread. So the new plan, and this is typically the plan with any compute shader wants to utilize shared memory, is to designate a main thread to do the global atomics. So that thread will still experience the latency of doing global atomics, but it won't experience the serialization of a whole bunch of threads doing global atomic increments. So designate one thread, thread 0, and that will be the thread that does the global stuff. Yeah, so the plan is to record in shared memory that this thread, the current thread wants an index when determined its particle will be freed or drawn. And later, the main thread will request basically all the indices that were requested by thread in that thread group. If there's any questions, please let me know, because like, not sure if my explanation is getting through.
Like this kind of thing is like you have done it before, then you understand, otherwise you don't. I definitely don't understand this until I actually write code with shared memory.
Okay.
I'm sorry for me.
Maybe the code will be more understandable. Although, it took me a while to understand this myself. So I don't feel bad if you if there's trouble understanding it. And also my explanation probably not optimal. But the idea is like, I have the whole shader here with the unimportant parts cut out. But the idea is that we're going to record how many threads want an index or request an index. And so at the beginning of our compute shader, we'll use the main thread to initialize this number to 0. And then we have a barrier, so all threads wait for this to actually be 0. So no threads race ahead and start doing stuff. And then in the actual, I guess, work of the shader, this is where we determine that if the particle just died, we just say we need a free index. We set this bool to true, and then we atomically increment a shared variable. So every thread that needs a free index will increment this. And similarly, for draw indices, we'll increment a shared variable, which is by the way, much faster than global atomics. That's another important thing, because we are actually doing more atomic operations, but since most of them are in shared memory, we still get a performance boost because shared memory is super duper fast. So after all the shaders, or all the threads are done requesting or incrementing, we wait. We have a big barrier right here. And then the main thread will use the requested amount to do an atomic increment on the free count and the instance count. So we'll basically, and you can think of this as allocating a region of memory, or we're saying we're reserving all these indices for this thread group or this work group. So the main thread will do that, and we'll put the start of the region into shared memory for each region that we're requesting. And then we'll wait again, have all threads wait for the main thread to finish doing that. And then finally, we can have each thread insert its index into the global memory. And doing an atomic add here because it's incrementing the start of the region. It needs to reserve a slot for itself. But since this slot is in shared memory, it's quick. And I think this might be a typo. I think this should say free index, and this should say draw index. Let's scroll up and see. Oh, no, it's okay. So this is the index of the particle. That's not a typo. So yeah, I hope that made sense to you guys. But I tested it and it works. Or it passes the eye test, I should say.
Just to try and see if I understand. So is this basically, instead of having each thread update the global memory, they first update a local shared memory between them that's fast but isn't shared between all threads, and then later like one master thread from each group will go and update the main global memory?
So yeah, GPU has this GPU has this concept of like a block, or I don't know what OpenGL terminology is, but it's a group of threads that run together and they share certain memories, and those memories are just like cache, they are fast.
Okay.
Yeah, so wave is another term for this. I don't know what OpenGL terminology for this is though.
So each wave kind of has its own, keeps track of its own index within the waves, and then once per wave, they'll go and update the global memory to kind of collect all of the waves together.
Yeah, that's pretty much what's happening. We're basically saying with this requested indices, the two requested indices variables, we're saying how much we're going to need eventually. And then the main thread is going to go in and actually request a block that's that large from global atomic memory. And then they'll put the start of the range that was requested into a shared variable for the threads to later use.
Which line does the main thread per wave request it from the global memory?
Right here. So we wait for all the particles to finish requesting with the barrier, and then the main thread does atomic increments on the global memory.
Okay.
It says I want this many free indices, And so atomic add increments, and it returns the value it previously was. So it gives us the start of the range, basically. And then if another thread group atomically increments, then it might get the start of the next range. But each thread group, basically, or work group, is reserving its own little chunk, pretty much.
Okay. Yeah, that doesn't make sense.
Yeah, it's just a weird programming model because you have to think both serially and concurrently.
Yeah, I find that tricky to keep track of it in my head, but this makes sense.
Oh, and there's also a nice explanation in chat. There's the classic use for shared memory, I think, or one of the classic uses is for generating a luminance histogram of all the pixels on the screen. So that usually involves incrementing, like every single pixel or every thread that increments on pixel will have to increment some atomic variable that says like how many particles of this brightness or how many pixels of this brightness appeared. But you can use shared memory to speed it up considerably.
It's good doing the same thing you do here, where you kind of add up all the pixels in the current wave, and then at the end of it, finally add the waves together.
I actually put I have to remember the strategy, but I actually have the code for it on the homepage
Okay.
of my blog for no reason particular. I just wanted to see how the code formatting looked, but it's actually really convenient for this discussion. Okay, so
yeah, this code formatting does look really good. I got it working.
Nice.
but yeah, we have a bunch of shared buckets because normally you have a histogram that holds a bunch of buckets, and each thread will determine which bucket to increment. But instead, we can increment buckets in shared memory and then have one thread. Is that what we do? It's so confusing. It's been such a long time since I wrote this. So we increment a shared bucket count. And then each thread. Oh, okay, then each thread does one increment on its assigned bucket. This is like the simplest use of shared memory and still kind of tricky.
Mm-hmm.
So yeah, and I have at the bottom of the second blog post a bunch of links to the code. And then I have some further optimization that could be done that I haven't implemented because optimization is an infinitely long endeavor. So we could have per emitter calling, we could generate a bounding box around each emitter based on acceleration, velocity, and position. And we can do frustum calling on whole emitters. And another thing is software rasterization for really small particles. Because if you have 10 million particles, chances are a lot of them are going to be super tiny, and it's really inefficient for the hardware to rasterize. Because the smallest thing that can be rasterized are 2x2 quads. So you end up with up to 75% of pixel shader work being wasted So we could do something like what Nanite does in Unreal 5, which is a hybrid approach where we rasterize big particles with the hardware rasterizer, which is what it's good at. And then small particles only take up a few pixels. We can rasterize it with a compute shader, but I think this is like in a league of its own. Like, you could probably spend way too much time working on a software rasterizer and compute. So that's more of like a funny thought than a serious thing someone should pursue. And another optimization that could be done is updating emitters at a variable rate, because emitters are really far from the camera. They don't impact the view as much. So you can update those at a lower rate. That's pretty self-explanatory. And then this isn't an optimization so much as a feature, but if you're rendering or if you're using particles for precipitation, like rain and snow, then with this system I have right now, the particles will just go through geometry because there's no collision. But what you could do to make it so indoor areas have no precipitation is to use a shadow map, and you can project the position of the particle into light space, pretty much, to determine if the particle is actually under something. So I think that might actually be something I add to my engine, because I don't like the look of particles going through walls and stuff and ceilings. And then of course you can add more features to these particles. You can easily add rotation, angular velocity, dynamic color, lighting, and so on. You just add more parameters to the emitters and to the particle structs, although keeping in mind, of course, how the data will be accessed, as I mentioned in the destructive arrays section. Otherwise your performance will degrade. Although, to be fair, any feature you add will degrade performance. It's just a question of how much you're willing to degrade performance for these features. And then finally, I mentioned using fewer buffers, because right now each particle emitter requires 5 buffers on a GPU. We need 3 just for particle data, because it's split into 3 arrays, and then we need what is it? The free list and the what's it called? In the indirect draw command. Wait, maybe there's 6 buffers, because we also need the draw list. Yeah, there's 6 buffers. That's even worse. But I don't know if it's actually a big deal to reduce the number of buffers per emitter. That's just something to contemplate. So you guys have any questions about this? Any thoughts?
I'm curious if you've done any research with like how this is often done in like AAA games or something, like if this is a common technique or things like that.
I've looked a little bit into how particles work in Unreal, but the difference is I think Unreal has multiple particle systems. There's like Niagara particles, which seem super complicated, like super duper complicated, because they have collision and they're like scriptable, and there's like a million parameters you can adjust. Like they go really deep. And the goal of this system that I made was to be simple, flexible, and fast. So yeah, mostly only know a little bit about how Unreal does particles. I'm not really aware of any other common technique games use. I guess mostly because particles are such a...
How about the...
Oh, sorry, you cut out.
Yeah, sorry. How about the non-Niagara particles? How do they work in Unreal?
My understanding is that Niagara particles are updated on the GPU, and they're actually stored, instead of being stored in a buffer or multiple buffers. Where'd it go? I believe the particles are stored in textures or just one texture. But I'm not sure the specifics of how they're updated.
I'm also not super familiar, but well, a little bit maybe. But as far as I know, the non-Niagara ones are updated on the texture. So you have a position texture, I recall. At the beginning of the frame, that one is updated. The textures are like maybe 256 by 256 or 512 by 512 at best, I think. Maybe 1K. Definitely not larger than that. But at the end of the, like towards the end of the frame around translucency, I think they get, basically those buffers are being utilized to draw them on the screen. So it's like a 2-pass kind of thing. But yeah, that's all I know.
Is that for non-Niagara particles?
Correct, yeah.
Okay, so I think Niagara particles must be updated on the CPU because they...
Niagara is compute shader driven.
Oh, really?
Again, yeah, it's all compute stuff. So these ones, the previous ones I mentioned are actually updated by pixel shaders. So Niagara is the new modern approach, and it's all GPU compute. I wouldn't be surprised if it has a toggle on CPU updating as well.
Okay, well that's pretty advanced then, because I've taken a look at the editor for Niagara particle, and it's overwhelming, and there's so much you can adjust.
I only know the frame capture side, so I have zero idea on the UI side of things, on the engine side. So yeah, that's my insight.
I'll just look it up right now. Yeah, they have just a million parameters you can adjust and checkboxes.
Well, that's really something.
Considerably more complicated than what I presented.
You know, MGUI has there's a couple of MGUI tools for node graphs if you want to get started.
Yeah, I've actually seen it, although I'm not exactly considering making a node graph editor for particles.
That might be a bit much.
Yeah, quite a bit of work for one person.
Yeah, absolutely, yeah.
And one thing that I don't plan on adding to my particles is collision. That seems too difficult, especially on the GPU. You'd have to upload like all the relevant collision meshes.
I wonder if, well, oh, you mean like with the ground? Okay, yeah.
Yeah, not with each other.
Right. With each other, it'd be, yeah.
Overloaded term.
Also for collision, you need to solve this kind of n-square problem. So kind of you need some kind of acceleration data structure, which is really hard on GPU.
Yeah, you could probably keep like a texture or some kind of like occupancy grid kind of idea.
Sorry, what was that?
I was just I was thinking, you know, like keep like voxels and put your particles in there, kind of give you an idea of occupancy. That might be one way to do it. I don't know.
Oh, for collision?
Yeah.
Oh, yeah. Yeah, I think eventually I am going to implement some sort of GPU voxel representation of the scene. So maybe I could do collision against that.
I know Nameless on the graphics programming server, that's how the GI and ambient occlusion is working, is using a voxel representation. It's actually a very neat little way that it's generated too. It's from view fragments.
Yeah, so he voxelizes the scene with the fragment shader, right?
Right. Yeah. He does image rates at the normalized device coordinates, or some translated version of that.
Yeah, I think that's a standard way of voxelizing scenes.
Oh, okay. I wasn't familiar. I thought it was a really neat approach.
But it is interesting because he is also his scenes. Some of the scenes are like literal Minecraft.
Yeah, that's what confuses me. It's like, you know, if you maintained an actual Minecraft model, you know, on the CPU side, you might get away with, you might do a little better. I don't know. If you had the voxel data.
If you want it to work with like all scenes, then
right,
using the raw Minecraft data might not be viable.
Exactly. Yeah. So you've got to kind of go, you pick a direction there, or not.
Yeah, I hope this talk was a little bit informative.
Yeah, it's insight into some things I've really never touched. This is you've got very deep knowledge of architecture here.
Yeah, I was hoping to shed a little bit of light on like shared memory and other. Basically, just try to touch on multiple things that some people might not have considered before.
Yeah, that's awesome.
And also, your packing and unpacking is pretty cool. Never even considered doing this kind of stuff.
Yeah, I appreciate the more info on compute shaders and stuff, because I feel like most of my graphics knowledge is so far just kind of technique and not really working with GPUs. So I find this stuff super interesting.
Yeah, and my knowledge is a little bit inverted